Hello viewers, my name is Dr. Ajay, Associate Professor in the Department of ECE from Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss the course Antennas, Waves and Propagation, and the topic which we are going to discuss today is the sources of errors in antenna measurements, fields and the coordinate system used in the for antenna measurements. So today's topic is the sources of errors in antenna measurements, fields and also the coordinate systems. These are the three topics which we are going to discuss for the today's session. Let us start our session. So here, whenever we design an antenna, we need to measure some parameters like gain, half power beam width, the antenna efficiency, radiation intensity, gain, pattern, polarization, bandwidth, beam width. So all these things are necessary parameters for us to measure the antenna that we designed. So in order to measure these parameters will judge the performance of the antenna. So if you want to judge the performance of the antenna, we need to measure these parameters. To measure these parameters, we need some instruments. We need some measurement techniques to measure these parameters. So antenna measurements are needed to know the actual performance of the designed antennas and also where they have to be used. So for every application, there are different types of antennas have been designed for various applications, and depending upon the performance or depending upon the efficiency of the antenna, so we need to select that particular type of antenna for a particular application. So there are no any accurate antenna measurements practically. So ideally or theoretically, we can have accurate measurements. So these theoretical concepts can be used to estimate or predict the signal performance, actual performance of the antennas in terms of gain, pattern, polarization, bandwidth, and efficiency. So there are various measurement techniques for us to measure these parameters like gain, pattern, polarization, the radiation pattern, the polarization, bandwidth, and efficiency. As we have studied in the previous sessions, the basic definitions of gain. From the basic definition of gain, the maximum radiation intensity, the ratio of the maximum radiation intensity of a test antenna to the maximum radiation intensity of an isotropic antenna is known as gain. It means that for measuring the parameter gain G, we are going to take a test antenna and also an isotropic antenna. That means the gain of an amplifier is different from the gain of an antenna. So for measuring the gain of an amplifier, just we calculate by output by input. But whenever we want to measure the gain of an antenna, we need two antennas. One is the antenna that we have designed, which we call it as a test antenna, and the other one is known as the isotropic antenna or other antenna, which is known as a reference antenna. So based upon these two antennas, we are going to calculate the radiation intensity, and the ratios of radiation intensities gives us the gain of the respective antenna that we designed. And similarly, the radiation pattern. So radiation pattern is also another important parameter which will decide the performance of the antenna. And the polarization. So polarization means the variation of electric field strength with respect to the surface of the earth. We call it as the polarization. So whenever we want to check the performance of the antenna, we need to know whether the antenna has been vertically polarized or horizontally polarized. So vertical polarization means if the antenna is if the electric field strength of the antenna is perpendicular to the surface of the earth, then it is known as the vertical polarization. If the electric field of the antenna that we designed, the electric field strength is perpendicular to the surface of the earth, then it is called as a vertical polarization. And horizontal polarization means if the electric field E is parallel to the surface of the earth, then it is known as horizontal polarization. So we need to measure the polarization also, whether to check the performance of the receiver antenna. So polarization is a technique which is measured the performance of the receiving antenna. Why? Because both the antennas must be either vertically polarized or both the antennas must be either horizontally polarized. If the transmitting antenna is vertically polarized, and if the receiving antenna is horizontally polarized, then there will be some deviation in the absorption of the signal at the receiving point of view. So hence the polarization, it's a method, it's necessary for us to determine, is the most important parameter for us to determine the performance of the antenna. And also the antenna efficiency. So we need to measure the antenna efficiency also. We need some separate measurement setup. So basically we know that the power radiated by the total input power is known as the antenna efficiency. So the antenna efficiency is defined as eta is equal to input power by total input power. So the input power, the power radiated to the total input power given is known as the antenna efficiency. So there are other parameters which will decide the performance, half power beam width, and also the beam efficiency. So all these decide the performance of the antenna, and there are some separate methods for us to determine these measurements. Let us start with the basic concept of the antenna measurement. So how to measure, what is the setup required for us for measurement of radiation. The most common antenna measurement is to measure its radiation properties like directional pattern, gain, or phase pattern in the far field. So as we already know, there are three types of fields. One is the near field and the far field. It means that the far field is some observation point at infinity where the actual radiation pattern is found. The actual radiation pattern where the electric and the magnetic field components are orthogonal to each other, it is observed only in the far field only. So whatever the parameters and the characteristics which if we want to find out, all those characteristics we can find out only from the radiation pattern which is drawn in the far field only. So the radiation pattern, the gain or phase can be recognized only in the far field only. Typical configuration of the measurement of radiation is shown in the figure. As shown in the figure, we can see here AUT. AUT stands for antenna under test. AUT stands for antenna under test. And there is a source antenna here. You can observe in the figure here, there is a source antenna. And here at the center, we are locating at the center of the XYZ plane, we have located antenna under test. Antenna under test. So as shown in the figure, we can perform the experiment based upon these two antennas. The basic procedure is to place the transmitting or the receiving source antenna at different locations with respect to the antenna under test, and thus getting a number of samples of a pattern at different locations. It means that if we want to test, if we want to measure some parameter, so what we need to do is we take two antennas. One antenna is fixed, it is stationary. The antenna that you fixed, it is known as AUT, that is the antenna under test, as shown in the figure. So this is let us assume this as a transmitting antenna. And let us assume one source antenna is there here. The source antenna is there here. And this is the receiving antenna. Let us say this is the receiving antenna. Now the transmitting antenna is fixed. Now what we do is the source antenna has to be moved slowly around the transmitting antenna in the XYZ plane. This source antenna, the receiving antenna, has to be moved slowly around the XYZ plane. And at different locations and at different points, we need to measure the electric field strength observed by this source antenna from the AUT. And see that this AUT, that is the antenna under test, it has to be directed directly towards the source antenna so that more amount of field strength is observed to the source antenna. So here what we need to do is, the source antenna is a receiving antenna here. This source antenna at this location, we need to find out the value of E. And at another location, you need to find the value of E. And at different locations, you need to find out the value of E. That is the electric field strength observed at a particular distance of R with respect to the source antenna. So what is that electric field strength? All those electric field strength readings has to be recorded manually. So after noting down all the readings of the electric field strengths at the source antenna, a radiation pattern is drawn by taking all the maximum and uniform field strengths at different points around the AUT. So around the AUT, we are going to find out all the points, like suppose it is 5 volts. Here the electric field strength is 6 volts. And here the electric field strength is it is 7 volts. And here the electric field strength is 6 volts. So like this, different field strengths are recorded. And all the field strengths which are maximum and uniform, all those points are considered, and we need to draw the radiation pattern. And from that radiation pattern only, we need to derive some parameters which will decide the performance of the antenna. So initially, before when design an antenna, we need to perform some experiment on the antenna. We need to perform some experiment on the antenna before launching the antenna into the market. So we need to test the performance of the antenna in a closed chamber, which we call it as any choice chamber. So all these arrangement, all this setup, that is antenna under test and the source antenna, whether it may be a transmitting antenna or the receiving antenna, experiment must be performed in a without any disturbances from the atmosphere or environment or from industries or human resources. So we want to find out the performance of the antenna in a closed room, which we call it as an any choice chamber. Any choice chamber. So this is the setup is selected in the any choice chamber, and we need to record all the readings, and we need to draw the radiation pattern, and from that radiation pattern we need to draw the parameters. The antenna under test can act either like as shown in the above figure. You can see here, this is the antenna under test. It can act as a receiving antenna or a transmitting antenna. So in the previous slide, you have seen this is the transmitting antenna and this is the receiving antenna. Also, we can also modify this as antenna under test as the antenna under test as receiving antenna. So we can place here the receiving antenna. Now this becomes the receiving antenna. And let us say this is the source antenna. Here the source is the transmitting antenna. Here the source is the transmitting antenna. Let us repeat the same experiment again. That is, here the source antenna acts like a transmitting antenna in the case 2. And the AUT, that is, this is AUT, this is antenna under test. It acts now like a receiving antenna in the XYZ plane. Locate this in the XYZ plane. And the source antenna is located exactly at the origin, which acts like a transmitting antenna, which is stationary. Now this receiving antenna has to be moved slowly with respect to the transmitting antenna. The transmitting antenna, the radiation from the transmitting antenna must be aimed directly towards the receiving antenna, that is the AUT. So here, as the source antenna is fixed, we need to rotate on the observation circle. You draw an observation circle around the source antenna, and on that circle, let us move the AUT, that is antenna under test, at different points, and we need to denote the records. We need to record all the readings of the electric field strength at the different points over the observation circle. So this circle we can also call it as an observation circle. Observation circle. So on this observation cycle, the receiving antenna, what are the field strengths observed, we need to record all the readings. Based upon the readings that we obtained, we need to draw the radiation pattern. So this is a setup required for us to determine the parameter or to draw the radiation pattern of an antenna. Here the conditions to be satisfied are the media has to be linear, passive and isotropic. So the media must be linear, passive and isotropic. So isotropic means we already know that which radiates uniformly in all directions. And passive means which gets the signal from other source. So we know that here there is a receiving antenna and here is a transmitting antenna. And here we are giving the supply directly. That means some current is fed to the transmitting antenna directly. And from this radiation is going towards the receiving antenna. Here the receiving antenna is the passive element. Here the receiving antenna, we are not giving any inputs directly to the receiving antenna. The radiation is absorbed from free space to receiving antenna. So receiving antenna may be treated as the passive element or the passive antenna. And the media must be linear. The media must be linear. That means the electric flux density must be proportional to E. So D must be proportional to E. Then we can say the media is said to be linear. and see that the EMFs in the terminals of the interchanged antennas are of the same frequency. So whether according to the reciprocity theorem, whether the antenna acts like a transmitting antenna or the receiving antenna, we need to apply the same type of EMF. We need to apply the same EMF which we have tested in, which we have performed the experiment in case 1 and case 2. Suppose if we say, for example, suppose here some terminals 1 and these are terminals 2, some EMF is induced here. What is the EMF? Electromotive force. Let us say 3. Let us say 3 volts of EMF is applied here. And we need to calculate the current at the terminals of the antenna 2. We need to calculate the terminals of the, current at the terminals of the antenna 2. Let us say this is the transmitting and this is the receiving antenna. Now let us calculate the current. What is the current at the terminals of antenna 2 as I2? So I2 represents the current captured or the current that is being observed at the terminals of antenna 2 due to the radiation that is happening from the transmitting antenna 1. And let us say, in another case, the EMF, let us say this is 2 and 2 dash, and 2 and 2 dash, here there is an EMF of 3 volts and calculate the current I1 here. So in case 2, let us say the transmitting antenna has been shifted to the terminals 2. Terminals 2, the transmitting antenna is shifted, and whatever the EMF we applied in the case 1, same amount of EMF has to be applied in the case 2 also, whether the antenna acts like a transmitting antenna or the receiving antenna. So in the earlier case, we have applied the EMF of 3 volts. Similarly, the EMF of 3 volts has to be applied for the antenna for the terminals 2, and current has to be calculated at the terminals of antenna 1. So whenever the EMFs in both the cases that we applied is same, then the current absorbed in the terminals either in the case 1 or the case 2, I1 will be equal to I2. Hence the reciprocity theorem will be satisfied. Hence this is known as the reciprocity theorem. The power flow must be same in either direction. So these are the 3 requirements for us to satisfy the reciprocity theorem. So according to the statement of the reciprocity theorem, so what does reciprocity theorem says? If an EMF is applied, suppose this is 1 and 1 and this is 2 and 2 dash, 1 and 1 dash, this is 2 and 2 dash. If an EMF is applied at the terminals of antenna 1 and current is calculated at the terminals of antenna 2, and if EMF of E21, this is EMF of 1 2, let us say EMF of E12, this is 1 1 dash, let us say this is case 1 and this is case 2. So for case 1, let us say EMF of, let us say the EMF of E12 is applied at the terminals of 1 1 dash, then calculate the current I2 at the terminals of 2 2 dash and note down the current, what is the amount of current at the terminals of antenna 2. Similarly, in case 2 here, apply the EMF of E21 at the terminals of antenna number 2 and measure the current I1 at the terminals of antenna 1, at the terminals of antenna 1 1 dash. So I1 will be equal to I2. I1 will be equal to I2 only when E12 is equal to E21. That means if we apply the same amount of EMF at the terminals of 1 1 dash in case 1 or at the terminals of 2 2 dash at case 2, the currents produced I1 will be equivalent to I2 in both the cases. So this is known as the reciprocity theorem. So in standard careful measurements, the first condition can be satisfied always and the second can be met without problems. The third condition is the most difficult and may lead to the statement that there is no accurate antenna measurement. So these are the 3 conditions. That means the media must be the linear, passive and isotropic. The EMFs must be changed with same frequency. The EMFs in the terminals must not be interchanged. That means the EMFs must be same. And also the power flow must be same in either directions. So these are the 3 conditions to satisfy the reciprocity theorem. So In standard careful measurements, the first condition, that is the linear isotropic passive, is satisfied always for any type of parameter calculation, and the second may be met without problems. The third condition is the most difficult and may lead to the statement that there is no accurate antenna measurement. So out of these three conditions, the most popular one which will satisfy at all times, at all conditions, is the first one, which is the linear isotropic and passive medium. So that is about the antenna basics and antenna basic setup required. Let us go for the next topic, that is the near and far fields. Near and far fields. So whenever we place an antenna at one particular point, there are three zones which are surrounding the antenna. There are three zones which are surrounding the antenna. The first one is a near field zone. The second one is the radiative field zone. And the third one is a far field zone, reactive zone. The first one is a near field zone or inductive zone. The second one is the radiative reactive field zone, and the third one is a far field zone. So out of these three zones, which zone we need to select for antenna measurements? For finding out different parameters. So which zone is preferable and which zone is not preferable, and what are the reasons behind it for selecting the far field, and what is the reason behind neglecting the near field? See, there are three different regions, right? So when we can say an antenna is in the near field region. Suppose if this is an antenna, this antenna immediately is surrounding some zone here. There is one circle here. If this distance is r, if r is less than 0.62 into root of L cubed by lambda, then that zone we call it as the first zone, that is the near field zone. It is known as the near field zone. It means that the first zone has a lot of inductance which surrounds immediately around the antenna, and no electrical and magnetic field components are formed in this near field region. And these electrical and magnetic field components are not formed and also not perpendicular to each other. The radiation pattern will be non-uniform. It is irregular in shape. So if the radiation pattern in this zone, in the near field zone, it will be like this. It has no any definite shape. The radiation pattern has no any definite shape. It is non-uniform. It is irregular shape. So this is how the near field is created at a distance of r less than root of L cubed by lambda, where L represents the dimension of the antenna or the length of the antenna. If we say this is the dipole antenna, and this region represents the L value, that is the length of the antenna. Or if this is the half-wave dipole antenna, we can write as L is equal to lambda by 2 antenna. And surrounding this region, this is the first region, we call it as near field region. And the distance up to from here to here, we call it as the R. It represented as R, the distance. And if distance is less than 0.62 into root of L cubed by lambda, we call it as a near field region. And similarly, there is another region which is also known as the radiative reactive zone, which is in the second zone. This is the first zone. This is the second zone, and this is the third zone. So this is 1, this is 2, and this is 3. So this is the condition for the second zone, and this is the condition for the first zone. If the value of r lies between 0.62 into root of L cubed by lambda and 2 L square by lambda, then that zone we call it as the radiative reactive zone. In this second zone, the formation of the radiation pattern begins. The formation of the radiation pattern begins. The electric and field components are also visible, are also formed, but not orthogonal to each other. That means the electric field and magnetic field components are formed, but are not orthogonal to each other. So here, this is the condition for the radiative reactive zone. And if R is greater than 2 L square by lambda, then that region we call it as a far field region. That is 2 L square by lambda. If R is if r is greater than 2l square by lambda, then this condition we call it as the far field region. Then this condition we call it as a far field region. So these are the three regions. In the far field region, so what we can observe is a uniform radiation pattern is observed. The major lobe of the radiation pattern is clearly observed. The electric and magnetic field components are clearly observed. And also the electric and magnetic field components are perpendicular to each other. So as the radiation pattern is very clear and uniform, and it is maximum, the major lobe is maximum. So we can derive many characteristics and parameters from the major lobe of the radiation pattern only in the far field region only. So we are going to consider only when r is greater than 2l square by lambda as a far field region, and in this region only we are going to find out all the characteristics of the antenna. So here you can see here there are coupling and multiple reflections. That means in the first zone, that is in the near field zone, where the distance is very less. The coupling and the multiple reflections and the inductance will be more. If the two antennas are placed very near to each other. These things will happen. That is, the inductance is more, coupling will be more, and the reflections will be from transmitting antenna to receiving, and the receiving antenna to the transmitting antenna. The main disadvantage of far field is the required large distance between antennas, leading to large antenna ranges. So because of the large number of advantages, most of the cases of the measurement will be done in the far fields only. So you can see here in the reactive near field, the radiation pattern is irregular in shape. It is not formed here. In the radiative near field or radiative reactive field, the formation of the radiation pattern begins. And in the far field, you can observe here, the radiation pattern is formed clearly. As one lobe. This is known as the major lobe. We'll see the coordinate systems. We need to represent. So the antenna is measured only in the three-dimensional plane only. So we need to have some basic concepts about what is the coordinate system. So what is this theta is equal to 0 plane? So what is this conical plane? So we need to study some important angles to represent the antenna in the three-dimensional plane. So as we already know that when we place an antenna at the center of the circle, the upper portion, that means if we have this is y plane and this is z plane and this is x plane. So the upper portion, that is the yz plane, represents the theta angle, or we can also call it as an elevation angle. We can also represent as elevation plane. This zone we call it as elevation angle or elevation plane. And below, that is the xy plane. The xy plane is known as azimuth plane. This is azimuth plane, or the angle we represent as pi. The pi is known as the azimuth angle, and the plane is known as azimuth plane. And there is one more angle which is known as the polar angle. It means that any point, if you take any point like r comma theta, from the center of the origin, at a distance of, calculate the distance of r, move any point p from y to the z in anti-clockwise direction. And there is some angle is found here, theta. We call it as a polar angle. So if you take here, some r is the distance. If you take a point here, you move the point in the yz plane in the anti-clockwise direction, some angle is formed. That angle we call it as a polar angle. And there are two principal cuts. There are two types of principal plane cuts. That means exactly at the latitude, exactly at the longitudes, there are two principal plane cuts. We call it as principal cuts. And the next topic we will see the sources of errors in antenna measurements. So whenever we have designed an antenna, we are going to check the performance of the antenna. Even we check the performance of the antenna, we get some errors. So what are the reasons what is the reason behind it for getting the error? The error may be either the transmitting antenna. We can get errors while measuring the gain of the receiving antenna. Suppose if we take a parameter like gain, suppose our goal is we know that the gain is 5 dB. The gain of the transmitting antenna is equal to 5 dB. But after designing the antenna, we got the gain as only 4 dB only. So what is the reason behind it? So why we are getting the gain as 4 dB? So our requirement is gain must be 5 dB. But what the value we are getting is we are getting 4 dB. So why we are getting the gain of the antenna that we designed as 4 dB? What's the way the problem lies? That means whether the problem lies in the design of the antenna, or whether the problem lies in the measurement setup, or whether the problem lies in connecting the antenna to the total setup. So all these has to be considered. These are known as sources of errors in the antenna measurements. So there are different sources of errors in the antenna measurements. The first one is errors due to finite measurement distance between the antennas. The second one is reflections from surroundings. The third one is errors due to coupling in the reactive near field. The fourth one is errors due to misalignment of antenna. The fifth one is errors due to man-made interface. The sixth one is errors due to atmospheric effects. The seventh one is errors due to cables, errors due to impedance mismatch, and errors due to imperfections of the instrument. So we'll see one by one. So what actually this finite distance measurement of antenna means. So errors due to finite measurement distance between the antennas. We can place the receiving antenna closer to the antenna. We can also place the receiving antenna at a far distance from the transmitting antenna. If the receiving antenna is placed very closer to the transmitting antenna, some types of errors will occur. So those errors are known as quadratic phase errors. So when the distance between the antennas is very small, then the field received by the AUT, that is the field received by the antenna under test, which is known as the receiving antenna, at different points will be different phases, causing a quadratic phase error. So this quadratic phase error affects by reducing the measured gain and increasing the side lobes. So when the distance between the two antennas is very less, quadratic phase errors will increase, as a result of which the minor lobes increase. Whenever we design an antenna, so we should be careful that the major lobe must be very high. The major lobe must be very high. At the same time, the minor lobes and the side lobes must be very less. So then only the gain of the antenna will be increased. So due to the small distance between the antennas, the amplitude is also affected. So whenever the distance between two antennas is very less, then the amplitude is also affected. So amplitude errors are of two types. One is a transverse amplitude errors. The other one is longitudinal amplitude error. So in transverse plane, the amplitude of the field is very small at the edges of the antenna under test, while slightly greater away from the edges. So this causes the transverse amplitude errors. So these are affected by the longitudinal amplitude errors. So typically the measurements for longer end-fire antennas are affected by the longitudinal amplitude errors. So here, in these sources of errors in the antenna measurements, the first one is errors due to finite measurement distance between the antennas. So we are getting two types of errors here. If the distance between the antennas is very less, we are getting a quadratic phase error. And at the same time, the amplitude is also affected, which we call it as the longitudinal amplitude effect errors. And these longitudinal amplitude errors have a major impact for long distance communication. In the end-fire antennas. If you select a particular type of antennas like end-fire array antennas, this amplitude error is it causes serious distortion of the signal. The second sources of error is the reflections from the surroundings. So we know that there are many surroundings. There are many ripples. There are many industries around the surroundings. There are many trees There are many large industries and buildings we are having from the surroundings. So whenever we transmit the signal, these signal fall on the buildings and trees and are reflected in different directions. That means the electromagnetic rays fall on the obstacles, they are reflected and refracted in different directions. So the reflections from the surroundings is another important source of the error, because reflections cause amplitude ripple as well as the phase ripple. That means it will have an impact on the amplitude and also at the same time the phase of the electromagnetic wave will change, and also at the same time the velocity of the wave will also change. So the ripples occur in a region due to interference between the direct wave and the reflected wave. So we can see here, if you take a transmitting antenna, I suppose there is a building here, and a signal is transmitting directly. This is known as the direct wave. It touches the building directly, and it reflects in different directions. It reflects in different directions. So these are known as ripples. That means the ripples occur in a region due to interference between the direct wave and the reflected wave. The powers of the waves are not added, but always the field of the waves are added. The third one is errors due to coupling in the reactive near field. So as we have seen that when the distance between the two antennas is very less, or R is less than 0.62 into root of L cubed by lambda, this is known as a near field region. Here the reactance will be more, so there is a chance that coupling errors will occur when the distance is finite, when the distance is very less between the source antenna and the destination antenna. The reactance near field causes significant error at low frequencies. If the distance is greater than 10, then the coupling is negligible. So errors of coupling occur when at low frequencies only and not at the high frequencies. And the fourth one is errors due to misalignment of antennas. So whenever we are going to fix an antenna to the cable, we need to check whether this antenna has been connected tightly or not. That means the antenna measurement is a three-dimensional vector measurement. So exactly the antenna has to be aligned with respect to the cable properly, and the contacts must not be loose. There must not be any loose contacts between the cable and the transmitting antenna, either at the transmitting section or at the receiving section. So due to this misalignment also, the pattern cut cannot be properly taken. That means a clear-cut radiation pattern may not be detected at the receiving antenna. Errors due to man-made interface. So we are having two types of ranges, that is the outdoor ranges and the indoor ranges. So when the man-made interference gets coupled with the receiver at the frequency same as the measurement frequency or any other frequency, the harmonic distortion takes place. Errors due to man-made interface means there are many types of vehicles going on the roads, and there are many industries and there are many factories around the surroundings are there. So from this also some sort of disturbances occurred while the signal is being transmitted from the transmitting antenna to the receiving antenna. So these types of disturbances occur in the outside environment only, not in the indoor range. In the indoor ranges, in an uncharged chamber, the reflections from the walls, floor, and ceiling are significant. So whenever we are going to test the performance of the antenna, we can test it either in the closed room or in the outdoor environment. So if we want to test the performance in the indoor, that is indoor environment, that is an uncharged chamber, there are some reflections from the walls, floor, and ceiling. Hence, we cannot get the exact value what we are expecting. At the same time, in the outdoor range also, whatever the expected value that we want, we will not get the signal to the receiving antenna due to the disturbances from the surroundings. So errors due to the atmospheric effects. So this is also one of the reasons. Due to the atmospheric effects such as variation of the refractive index of the atmosphere, sometimes there will be sudden rain. Sometimes after some time interval there will be some hot sun will be available here. So at one region there will be heavy rain, at one region there will be no rain. So the wave travels from one region to other region. So the density of one region will be different from the density of other region. As a result of which the refractive index will vary. So whenever the refractive index varies, that is the electromagnetic wave is traveling from a rarer medium to the denser medium, definitely the velocity of propagation of the electromagnetic wave will decrease. So these are known as the atmospheric effects. So there are different layers in the atmosphere, out of which this electromagnetic wave travels through different layers in the atmosphere. So in every layer, the velocity of propagation of the electromagnetic wave will be decreasing and increasing. As such, the amplitude will vary. and the signal which has to reach to the receiver may not reach instantaneously. It will reach after some time delay. So definitely due to this reason, there will be some error while measuring any parameter of the receiving antenna. So due to the atmospheric effects. So errors due to cables. If the cables used for connection are not very good, that means if the shielding is not good, if any leakage is occurring at the cable, if the cable is damaged, then definitely we are not going to get the desired value of the desired value of the receiving antenna. So whenever we are going to sell the cable, see that the cable must be properly shielded, no leakage is there. Errors due to impedance mismatch. So if the antenna impedance is not matching, more amount of power we cannot transfer between the transmitting antenna and receiving antenna, and more amount of power will not be absorbed by the receiving antenna. Suppose if the antenna and the cable impedance are mismatching, that means suppose let us say the transmitting antenna impedance is 75 ohms, and if the impedance of the cable is 50 ohms, that means there is a mismatch. So either we should change the cable or we should change the design of the antenna. We need to change either the cable to the 75 ohms or we need to change the design of the antenna so that the impedance of the antenna is 50 ohms. So either of these we need to do. In the necessary changes has to be made for impedance matching. So unless and until there is impedance matching is not there, then we cannot get a desired value of the signal at the receiving point of view. So impedance mismatch is one of the major problem while measuring any parameter of the receiving antenna. So either the receiving antenna also, the receiving antenna and the cable, the impedance must be matching should take place. So errors due to imperfections of the instruments. So the last one is errors due to the imperfections of the instruments. So due to imperfections of the instruments in the measurements such as transmitter, receiver, positioner, the measurement errors occurs. So whenever we are going to design an antenna, according to the application point of view, we need to design the instrument exactly and perfectly. So sometimes we design the antenna perfectly, but the instrument that we are going to measure may not work properly. So there may be some measurement error problems from the instrument point of view also. So whenever we are going to measure some characteristics of the antenna, so we need to take a proper instrument which is working perfectly. So due to the imperfections of the instruments also, there will be some error getting either at the transmitting section or the receiving section. So these are known as the measurement errors. So these are the different types of sources of errors in antenna measurements. So with this, we'll close this session. We shall continue in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.